recording. Okay, so you'll see charts like this in chemistry class a lot. We call them flow charts, and they're used to separate information or things that are all together or ideas into separate parts. So if you discover matter when we want to separate it, you basically have the first question: does it have constant properties and composition? If the answer is yes, then we know it's a pure substance, because that's what constant properties and composition means. Then we would ask ourselves, all right, can it be simplified chemically? And if the answer is yes, then the substance was a compound. If it's no, it's an element, right? If the answer to the first one was that it was not, so then we're talking like trail mix or something you might remember, then we had a mixture, all right? And we would ask ourselves, is it uniform throughout? Then if the answer is no, it's heterogeneous, because that means more than one. Yes, it's homogeneous, and that means only one. You okay with that? All right. So it says, lastly, depending on its properties, a given substance can be classified as a homogeneous mixture, a heterogeneous mixture, a compound, or an element. These are basically the four ways we will describe things. And it is kind of hard once in a while to tell a homogeneous mixture from a pure substance. So like there's a lot of similarities there. But if it's on a test, it will be obvious like which thing it will be. You okay with that? Okay, so right over here, let me turn the lights back on. Oh boy, you owe me a new one. Right over in front on that lab table is a little thing we can use to demonstrate this. So if I come across this container, so I look at it and I think, all right, tell your partner, does it have constant properties and composition? Does it look like it has more than one thing in it? Okay. Is there parts of it that are different than other parts? It's just a green liquid, right? So I would say it does have constant composition. There's not like chunks of something here and over there. So now it's just water with food coloring in it. I've added one more thing so this thing will work. But we're going to say, all right, this looks like a pure substance. There's nothing definable in here to separate it into its parts. So now, can it be simplified chemically? So if you're a note taker, I would draw this picture real quick. Yes, ma'am. Okay, they're right over here. One for you and him, or do you need more? All right. So don't take like 5 minutes to draw this. Take about 30 seconds. And you can label this. This is an electrolysis device. Electrolysis, if you want to spell it right. Now, whenever we use a certain apparatus in AP chemistry, you should draw and label it, because if you take the test normally, which we hopefully will, you'll always have a question that's lab-based, and they'll very often, one of the parts of the problem says draw the apparatus. And you get a point literally for drawing a picture. While you're drawing that, I'm going to turn the electricity on. And you will see that it starts to bubble right down here, what we call the electrodes. And we'll talk about that bubbling. right there. Thank you. That's what I thought. Okay. So what I've done is I've taken this pure substance and I'm seeing if I can separate it or simplify it chemically. What's going on here is I'm passing electricity through this liquid. Now that's why I had to add, it's not pure water, I added a little bit of acid to make the water conduct. But as I do so, and you may not see it very well from the back, but there's bubbles being produced down here that are floating to the top. And I will let this go for a few minutes and we'll just keep on talking, but kind of glance up here once in a while and look at how much gas is collected on each side. And we're going to talk about that. So what I'm doing is I'm using electrolysis, which is a chemical reaction to pull water into its constituent parts. And that would be the oxygen and the hydrogen. So my pure substance, I'm now separating into elements. You okay with that so far? Okay, I'll let that go and we'll come back and talk about it in just a little bit. Now, learn the term lysis in science means to tear apart or to separate. So I'm tearing the water apart using electricity when I do electrolysis. All right, so anyway, we'll come back to that. There's that slide. Let's do this. Okay, I'm not gonna have or give you time to write these down, but an atom is the smallest thing an element has that has the properties of that element and can enter into a chemical combination. So if we talk about a single piece of an element, we're talking about the atom, right? Then the molecule, it consists of two or more atoms connected by strong forces known as chemical bonds. And we'll learn all about chemical bonds, just not today. But these are just keywords you really have to know. I will use the term molecule and compound interchangeably. They are slightly different, but it doesn't really matter. A molecule we usually talk about when two nonmetals are together. A compound we usually talk about when a metal and a nonmetal are together, but it doesn't really matter. All right, so this is elemental gold. And then you scan super in, you can actually see the atoms. Now, I don't have anything that can do that in this room. It would be millions of dollars, but that's what it looks like when you zoom in. The circles are literally the atoms that are lined up. Okay, then just like a cotton bulb. Here's the cotton. You zoom in and it looks just like your hair essentially. You zoom in even farther and it's overlap layers. Zoom in farther, you get the chemical structure, and then zoom in like the lattice is what they call it, structure. Zoom in more and you see the actual components. All these things are made out of basic building blocks that we call atoms. So here are some other examples. We'll just keep on going. And then here is the same thing I'm doing. This is talking about electrolysis. So the decomposition of water is shown at the macroscopic, that would be here. And then the microscopic, that would be, I guess, these. And the symbolic levels, which I don't actually, maybe it's not on the slide. The symbolic would just be H2O. And then your arrow to H plus and O2. That would be the symbolic, is where we write out the symbols. And then we'll just kind of get in the habit of balancing it. We need 2 oxygens, so I put a 2, 2, 1. Now, you don't have to know how to do that yet, but you do soon. All right, so the battery provides an electric current that decomposes the water. At the microscopic level, the liquid separates into gases. We can see that with our own eyes in front of us and on the screen. And then water just separates to H2 and O2 right here. Okay, try and remember this when I come back and we look at that. Okay, then a fuel cell, if you've ever heard of those, a fuel cell is exactly this same process, but it's in reverse. I let hydrogen and oxygen react, and as they react, guess what they produce? Water, yes, but something else. Electricity. Because think about science. If I'm putting electricity in to separate them, then when they come back together, they're going to give off current as well. It has to be the exact opposite. Now, it's not like you would think, like when water's formed, a big lightning bolt comes out or anything. But we can take advantage of the fact that oxygen and hydrogen exchange an electron. And that electron has to move, and we can use that movement to do work. So, anyway. Right, then just more compounds and elements. Almost 1/3 of naturally occurring elements are used to make a cell phone. That's pretty crazy. That's more elements than make you, way more than make you. And really, cell phones are very expensive, but for what goes into them, they are really cheap, to be honest. They take a ton of resources to produce. All right, now we're finally on section 1.3. And that's physical and chemical properties, which hopefully you learned in 7th or 8th grade, and maybe more. So you should be able to identify properties of changes in matter as physical or chemical, identify properties of matter as extensive or intensive. These are new words to you, and they're definitely important. Hopefully chemical and physical changes in properties are not new to you. All right, so the characteristic that enables us to distinguish one substance from another is called as properties. Like if we look at Cooper, he has properties. And most people, I didn't know him last year when he ran for office, but they said he's that kind of tall or medium height basketball player that always smiles. Like, oh, I think I know who you're talking about, because he's always smiling, right? So then Christensen, what's your first name? Misha. Like, I didn't know her, but I could see her and assume she was a Christensen because she shares similar properties to her sisters. All right, so we use properties all the time to like identify things. We're just going on a little bit more specific property. A physical property is a characteristic of matter that is not associated with a change in its chemical composition. Okay, so if I could change the property or observe it or anything like that, I shouldn't say change it, but if I could observe it without changing it, then it's a physical property. So like looking at this liquid, I could say that is green. By me saying it's green, did it change its color? No, all right? But if I pass electricity through it, something has changed. It's starting to produce gas on both sides and there's a little color change. So the observation of, hey, can this be pulled apart through electricity? That's not a physical change, because to figure that out, the whole substance has to change. All right, examples of a physical property: density, color, hardness, melting point, and electrical conductivity. There's way more, but that's just a few. And a physical change is a change in the state or properties of matter without any accompanying change in its chemical composition. So like if I tear a piece of paper apart, it's still paper. I just changed its shape, its mass, its volume, but I didn't really change the fact that it is a piece of paper. All right. So melting butter and boiling, stuff like that are physical changes. The change of one type of matter into another type, or the inability to change, is a chemical property. So what I'm doing up here, I'm changing water into different elements of H2 and O2. That is a chemical property. So flammability, toxicity, acidity, reactivity, and heat of combustion are some things that are chemical properties. This word right here, you'll learn it later, but it just means the energy it gives off when you burn it. So there's tons of examples of both, but just think, if it changed its chemical composition, it was a chemical property. If it didn't, it was a physical property or physical change. All right. What happened? There we go. So this is just kind of cool. Iron rusts, and that's one of its chemical properties, but chrome doesn't. That's one of its chemical properties. So we can use these, like we use lots of iron and steel when we build things, but then we always paint them. We cover them up with things so they're not exposed to the air, because iron's property is that it oxidizes. Chrome is on the outside of things. We don't paint over it. It's purposely on the outside so it looks shiny and it stays shiny. And that's because chromium, which is the main component of chrome, does not oxidize, meaning it doesn't react with oxygen and tarnish over time. All right. Then here's just some other things. We're just going to move on, and here we go. So after this slide, we'll talk a little bit about this over here. So these are new terms, unless you read. We have an extensive property. An extensive property depends on the amount of matter present. That is a big deal. We'll use that throughout the year. An example would be mass, volume, and heat. So about a month ago, I started a diet, and I've lost 16 pounds. We would just say I've lost mass. I don't know what I was in kilograms. But since I have lost some mass, my mass has changed. If it changes because I have less or more of it, then we call it an extensive property. An intensive property does not depend on the amount of matter present. And that would be like density or temperature. So I'm kind of a colder person in life. My body temperature is usually 97.1, year-round, every day, all day. I'm at 97.1. I was 97.1 when I weighed 200 pounds or 210, and I'm 97.1 when I'm 194. Because my body temperature does not care how big I am. It just cares that I'm a human and that the processes to run my body give off heat at about 97.1 degrees Fahrenheit. Density is really cool because it is made out of two extensive properties. We have mass divided by volume equals density, right? So we take two extensive properties and we can produce one intensive property. Now, will you think about that for a second and talk to your lab partner / neighbor / friend? How on earth can two extensive things end up being intensive? Ready? Go ahead while I turn the lights on and get this up. All right, any lab group think they have it and they're willing to talk? Nobody. Every teacher I've talked to so far at lunch or in the hall, they're like, I can't get the kids to interact with me this year. So it's like we lost the ability to communicate. All All right. What's that? Okay, go ahead. All right. That was perfect. That word proportionally. Absolutely correct. If you increase the mass of the substance, you have to increase the volume as well, right? So an easy example is when you take 1 penny and you find its mass, and then you find its volume, and you divide it. And then you take a second one, and it's really just 2 times the mass and 2 times the volume now. Well, it's the same ratio, right? Because the 2 over 2 just cancel out. Third penny, now it's 3 times the mass, 3 times the volume, and you divide them, and it cancels out over and over and over. So since they change proportionally, very good, then that means it's independent on how much they have. And that's how I memorized it when I was your age. Intensive is independent on the amount of matter present. All right? And then extensive, I didn't bother memorizing that. If I had 2 things that are opposite, I only have to memorize 1. All right, so here we go. Here's what I would like you to talk about with your lab partner as well. Oh, go ahead. Say that one more time, sorry. Yeah, we'll go over it, but heat is a measurement of energy and how much energy can be exchanged between a system. So like I touch this and it's cold to me, that's my heat being exchanged, a flow of energy. Now, we are used to just assuming that's also temperature. Temperature is a measurement of how much heat there is, but it's not heat. Does that make any sense? No. Right. So temperature, like that thermometer, when you put it into water, it's measuring how fast or slow the molecules are hitting it. Heat is the energy I could use from that flow of the change in temperature when the heat flows one direction or the other. Now, we will bring this up again, but that's the nutshell version. We're just used to them being the same thing. What's that? Absolutely. Yeah, so like a log, if I burn 1 log, I'll get a campfire for an hour, and they'll give me X amount of heat. If I burn 5 logs, it's now 5 hours with way more heat. But the temperature of the fire remains the same the whole time. So now I know temperatures get hotter and colder, or fires a little bit, but basically it's the same idea. Okay, will you discuss? There's something odd here. Discuss why is it the way it is? Talk to your partner. And you're like, I don't know what he's even asking. Well, get creative. Something is weird here. Something is odd. Talk to your partner about what's going on. Okay, there are 2 things to me that are different. All right, you nominate you, is that what you said? I like that nomination. Okay, well, at least 1 or 2. What's different? Okay, so there's a difference in the amount of gas produced, and the color changed. All right. Okay, let's hear it. So my left or your, like, the way you're looking at it? Okay. Okay, go ahead. Okay. So hold on, let me point. So you think this one is, and this one is? Who agrees with him? Does anyone disagree? Nobody? Yep, absolutely. Now, in here, there's no positive or negatives. They're now neutral. But in water, yes. Okay, now the color change is a lot harder to understand. Go ahead.
So like on the oxygen side, it's different because like it's oxidizing whatever is in there.
Absolutely. And it changes the pH of this solution. So this side becomes less acidic. This side becomes more acidic. Now, you don't have to really know that, but that's the things that are going on. We absolutely need to know the other part. Now, I want to make sure that we're clear on something, though, because most people think that it's because there's 2 parts hydrogen to 1 part oxygen. And that's sort of true, but it really is not true. It's because there are 2 parts hydrogen to 1 part oxygen. Like, wait a minute. That's the exact same thing, but it really isn't. When we separate these substances, let me make these blue. So I'll put a 1 here, a 2 here, and a 1 here. That's hideous, but just go with me. When we're looking at this, H and 2 O's doesn't exist. These are diatomic. And so when I balance it, it decomposes, one of them decomposes into twice as much hydrogen molecules as oxygen molecules. Now, it's a subtle difference, and if you don't understand that, it really does not matter. It's in the formula as well, but it's not always the exact same as the formula. All right, we have a chemical test we can do here to distinguish for sure that this is hydrogen and this is oxygen. I'm not going to blow it up because that would get me fired. But I'm going to light it on fire. Okay, so now this has the gas from that. And we'll light it on fire. Okay. So that made that noise. Yeah. Now let's check the other one. Then listen to this one. What does that one do? Same thing it normally does. It helped the match to burn, but that's it. So a lot of people, like, they think oxygen is flammable. Oxygen really isn't. It helps promote combustion, which is what the match is doing. But hydrogen definitely is reactive. That was a little explosion you heard, and it's little, because if I make it very big, the glass explodes. So don't ask, because then we're all dead. But that little pop you heard, it's pretty cool what it is. It's the reverse of that reaction. So that pop made what? I remade the water I just separated out. And it probably is already evaporated. No, it's there. You can see little water right there. There was no water before, right? This literally hasn't been used since a year ago, pretty much today. So I use a chemical process called electrolysis to separate hydrogen and oxygen into its components. Then I used a different chemical reaction to recombine them to make my water now. This one will also end up making water in the long run, because a match, when it burns, one of the products is water. So just not as much. Okay, cool with electrolysis? All right, let's move on, and we'll just keep discussing. You guys are pretty good. Hopefully you don't end up going wild, but hopefully we get more comfortable with each other, not scared that we're going to get each other sick or whatever. So hopefully these are solid. And we're going to spend an entire unit on the periodic table. So for right now, I'm not going to go into depth, but the periodic table groups elements together. They're arranged in increasing order of mass or protons. They're vertically arranged by their number of valence electrons. There's an unbelievable amount of ways that the periodic table arranges things. And what's crazy is that the periodic table was arranged like over 150 years ago. And all we continue to do when we find something new about an atom, all it does is say, yeah, it really does belong here. Like there's some crazy science about each atom, and all it does is confirm that the periodic table was arranged in a genius way. All right, measurement. This is where things get a little confusing. 1.4 through 1.6, but we'll get through them. All right, so I don't know. There's so much detail, but I'm going to blow through it. It is important to know this part. And be able to do these. And we're going to do a ton of these throughout the whole year. And if they're still confusing after today, then you're a normal human. If they make sense by the end of the day, then you're not normal. Congratulations. All right, so here we go. Measurements provide the information that is the basis of most of the hypotheses, theories, and laws in chemistry. So we perform a lab or something, we take observations, and those observations are really measurements. Then we can come up with ideas based on that. Every measurement provides three kinds of information. All right? One is the size or the magnitude of the measurement. And that's just simply the number that I write down. Next is a standard of comparison for the measurement. That means the unit. All right with that? Like if I just put 7, that means nothing to me. If I put 7 days in a week, like now it's something that I can have a frame of reference. If it's 7 miles per hour, I can kind of think, well, that's kind of slow. Unless I was running, that's pretty good. All right, so we need a unit so we know what the number is compared to in our world that we're used to living in. And then finally is an indication of the uncertainty of the measurement. This is the one that bugs high school and college kids. They're called significant figures, and it's just the number of digits in the number. So depending on how I report the value, it tells me how accurately I know that number. All right, so Jonathan, not picking on you, but Jonathan, will you stand up real fast? You're not in trouble. It's just a demonstration here. All right, well, everyone look at him and estimate his height and write it down on your paper. Just take a guess on how tall he is. Yeah, that's fine if you need a comparison point. So we definitely know he's taller than Bethany. Okay. So, all right, you can sit, but then tell us how tall you are. 6'4"? Oh, 6'1", sorry. How many of you were within 1 inch? So that's pretty much almost everybody. What's that? Who? Okay, so who was dead on? Okay. Now, if we just, in science, we can't just say that he's 6'1". That's why these are here. He's 6 feet and 1 inch tall. All right. If you went to Europe and you just said 6'1", they would think you meant 61 centimeters, and that wouldn't be very tall, right? So we have to put a unit on the end, 6 feet, 1 inch. And then this right here, he said 1-ish, right? You don't know exactly your height, and most of us don't. So like my sister will always report her height at 5 feet, 11 3/4 of an inch. You know why my sister always does that? Because I'm 5'11 1/2. Like she always likes to express her dominance that my life sucks and that she's taller than I am. But most of us don't put 1/2 or 3/4 because it's really not as certain as we would be saying if we put that little other part on. Does that make sense? Because very few of us have gone up to a real tape measure and found our exact height. We know we're just within an inch. Now, when we take a measurement with like a ruler, so don't mock my drawing skills here, or my speech impediment from 5th grade. Okay, so we're going to measure this thing from right here. Oh boy. And we'll say this is 1, this is 2. So we'll look up at this bar and we'll say, all right, it's 1 point something. And then I look like right here. And I know they're not to scale, but who cares? We'll just say it's past the second one, but not the third. So I'd say 1.2. All right, do I know anything more about that? No. So this is where kids get annoyed. Since I don't know anything more, the final value is my estimate. I'll say it's about in the middle. And then I need to know what this ruler is. You're used to inches, but in science we use meters or centimeters. So I'd say this thing is 1.25 centimeters. Now, a person looking at this number in the future, they would know the following. They would know you're measuring the length of something, and they would know the accuracy of the ruler was only to the tens place, meaning it had these lines on it, but nothing in between these lines, because they know this is your estimate.
How do you show that it's your estimate?
By it being the end. Whatever your last number is, it's always your estimate, and it means the previous numbers are the only known values. You can always guess. And the cool thing is, you could put a 1 through 9 right here and you're still right. Bravo. I can't hear with masks very well. Basically what?
Basically at the end of every measurement, you just try and do one smaller and just
Yep, pretty much. Okay, so now if, let's say I'm a kid and I feel like writing 1.25679. That would mean my ruler had the smallest increments ever because it'd be accurate to the 10,000th place. There's not a ruler on the planet that is that accurate, because the divisions between those lines, it would just look like a black dot. Okay, so we don't overstate our accuracy, and the way we know the accuracy, all right, or we know the uncertainty is actually how they put it, is the number of digits in the value. And we'll practice this through the whole year, so don't stress today. All right. So this is just kind of repetition, but without units, a number can be meaningless and confusing. This is the definition to me of math. In your math class, how often do they include anything identifying what the number's talking about? Rarely. And you never just randomly, unless you're super weird, walk down the street and just do calculations for fun, right? Life is a story problem. Once we put units on numbers, things mean something, and it's more visual. All right, we use the SI unit in chemistry. We have for a long time. So we don't use like inches or pounds or things like that, whatever. Okay, these are the ones that you should care about. You don't need to write them all down. If you want, you can take a picture, or just realize we're going to use these all year and they'll be really well ingrained, because we don't really care about length in chemistry very much. And when we do, we're talking about like angstroms, like things that are to the -10th. So don't stress much about length, but mass for sure, know the kilogram and gram. Time, that's easy, that's seconds. Temperature, our standard is Kelvin, which most of you probably aren't used to, but it's fairly simple. And then the amount of substance, this causes a ton of grief in life. We use a term called the mole. And a mole is just simply an amount of something. We came up with the idea, not we, I was not involved. Avogadro came up with the number. It's called 6.02 times 10 to the 23rd. If there are 6.02 10 to the 23rd things, we call it a mole. Why that number? Because he used gases and discovered that they all occupied the same value or volume at a certain temperature, and he did the math based on their densities and found out they all had that number. Now it's more accurate than that number because we round it, but they had this constant value for their same volumes, and we call it a mole. And it's short for molecules of gas is really what it's short for. But we can do it for all states of matter, but that was the original. It's kind of weird.
That's, if I'm not mistaken, that's everything, right? That's what everything is. Like, what everything in the universe is 6.02 times 2.
Anything you want. If I say that number, I have a mole of it. So it could be that many of us, that would be a mole. And that'd be a huge amount of matter. If it was that many things of hydrogen, it would be less than what I had in there. Like, but it's the same amount of things. So the mole confuses kids, but this doesn't usually. The number 12 is a dozen, right? It's a word I use to represent a number. A mole is just basically the same as a dozen. It's just a really big number instead. And since we don't, when we do math, we don't want to write this number out every time. We change it to the number 1, and it's a lot easier. So if we go back to this example, I'm really saying 2 moles of hydrogen react with 1 mole of oxygen to produce 2 moles of H2O. This number, math is easy, 212. That's a lot easier than this. Let's see. Plus this number, I'm not even going to do it, goes to that. So I don't know about you, but I like typing 2 into my calculator better than whatever this number would be. I don't even know the name of that number, but 2 of what a mole is. So it's a way to simplify the math, and it's a way to standardize each element on the periodic table. So like we say, you can't compare apples to oranges. That's true. But can you compare the mass of an apple to the mass of an orange? Sure. You can say, hey, that orange has more mass than that apple. Doesn't mean they're the same thing. We're comparing their mass. When we have everything in moles, it's a way to compare iron and hydrogen. They're super different in every possible way, but if I put them in moles, they are similar. Okay, I'm taking forever. Then when you go to college, you're going to hate this because they're going to make you do all sorts of conversions. But we simply really go milli and base and kilo. Those are really the only ones we care that much about in chemistry. There are definitely others, and it's just a movement of the decimal place. So if it says 10 to the negative 15 in your calculator, it would mean e to the negative 15 for most of you. That's what the e means. It means extended to the left 15 times. All right, so whatever, those are the standards, and I don't really focus on these until we do problems with them, and we just learn them as we do the problems. And then kilo, that's the big one we care about. This would say e to the third, and that would mean you move the decimal to the right, since there is no negative sign, 3 places. All right. Then I don't care about length. We don't use it. Kilogram, its original definition was the mass of 1 liter of water. They relate to each other pretty nice. Now this is actually out of date because just 2 years ago they changed the way they do this, but whatever. It's now defined as a certain cylinder of platinum iridium alloy which is kept in France. There's a big controversy among the nerds out there because the kilogram in France was weighed 2 or 3 years ago and it was no longer a kilogram. And they're like, the world has ended. Like, They don't know what to do. So they've redefined it, and it's like a super weird way. It's like how much it bends some sort of gravity, a particle or whatever. And you're like, well, okay. You nerds just keep getting more complicated. 1 kilogram is about 2.2 pounds. You don't need to know that. If this was on a problem anywhere, it would give you this ratio. Anyway, there's a picture of the kilogram in France. Well, it's actually a replica. There's 3 of them in the world, in case like the one in France gets blown up with a nuclear bomb or something. There's 2 more. What's that? I don't know where they are, but they're redefining everything based on math now, because math can't change. Okay, Kelvin we use a lot. I may do this incorrectly once in a while, but there is no degrees Kelvin. A degree symbol means you're relating it to something. Kelvin is not a relative scale. It goes to 0 and higher. So when you say degrees Fahrenheit, this is saying you're referencing the like whatever type of alcohol freezes at 32 or at 0, and where water's 32 and stuff like that. So there is no comparison, so we don't put that on there. The degree Celsius is also allowed in the SI system. We will use both, but it's super important that you know how to convert, and they're easy, from Kelvin to Celsius. Here's what's kind of cool. Celsius degrees are the same magnitude as those of Kelvin, but the 2 scales place their zeros in different places. So what that means is if I raise the temperature of water 1 Kelvin, then I would also be raising it 1 degree Celsius. But that liquid would not be at the same temperature. So one would be, let's say, 298, and then one would be 70, and one would go to 299, and one would go to 71. Okay, the change is the same, but the temperature is not. It's the same feeling. This is just room temperature, but they're just reported at a different base because the zeros are different. So water freezes at 273.15 and 0 Kelvin. So there's your conversion, or sorry, 0 Celsius. You take any Celsius value and you simply add 273. You can put the 0.15 if you feel like being extremely thorough, but you're not required to. So there you go. We use this number in chemistry tons and tons and tons, because that's the temperature they represent as room temperature. Oh, this was stupid, because that was Fahrenheit. I'm sorry. It would have been 25 to 26. It doesn't matter, but whatever. So if they ever say an experiment is done at room temperature and pressure, that means 298 and 1 ATM. We'll learn more about that. Time is a second, whatever. You can use whatever time you feel like. We can derive many units from the 7 base units. One is volume. And I don't stress how we derive volume, because it's actually extremely complicated. But just know that volume measures how much space something takes up. And this, you'll see often, a centimeter cubed and a milliliter are the exact same substance. So a milliliter is measuring how much liquid 1 cube, that is 1 by 1 by 1. That's the worst cube I've drawn in my career. If it's 1 by 1 by 1, that's a centimeter cubed, and that's how much volume 1 milliliter is. So you don't need to worry about that. I even deleted this slide that had way more data on it. All right, density we can calculate. That's mass over volume. The standard unit for density is kilogram per cubic meter, but we never really ever use that. We go grams per milliliter, unless it's a gas, and we go grams per liter. So yeah, it's right there, gases and then solids and liquids. So even though this is the standard, that's a huge number usually. Like if I take this he moved it. But lead is like 9 point something grams per milliliter. If I report that in kilograms per meter cubed, it's a humongous number. So it's just not one that's very reasonable. Okay. Uncertainty, accuracy, and precision. So counting is the only type of measurement that is free from uncertainty. Like if I count how many of you are in this room, I'm pretty certain that my number's right. There's not like a half or a third or a tenth of one of you floating around somewhere. You're all right here. The number of desks, that's an absolute number. But if I tried to measure the amount of molecules of air in this room, I would have to estimate because it can't be exact, because I'd have to do science in order to do that. All right, the result of counting is what we call an exact number. There are just a few other things that are exact numbers, and that would be when we define quantities. Like 1 foot is exactly 12 inch because that's how I define a foot. So it's important to know when a number is an exact number because we will not use it when we talk about significant figure rules, which can be complicated. All right, so if it is a given thing where you're counting or it's a defined quantity, then it's exact. Everything else has uncertainty in it. All right, quantities derived from measurements other than counting are uncertain to varying extents. These numbers are not exact. There are always practical limitations of the measurement process used. So like that ruler, we knew it was between 0.2 and 0.3, but we don't know exactly where it was. So that was uncertain. All right, a measured number must be reported in a way to indicate its uncertainty. We've already sort of said this. In general, when recording a measurement, you are allowed to estimate one uncertain digit. And in chemistry, you are expected to only estimate one. And like most AP questions are out of 9 points. And if you can get a 5 out of 9, you can get a 5 on the test. One of the 9 points is just simply if you wrote your number with the right significant figure. So if your answer on your calculator says 3.14159, but your problem, like that's your answer, but the problem only had something with 2 significant figures, then to get full credit, you would only put 3.1. That would be right. This would be right. This would be righter. Okay? You would miss 1 point from the 9 if you wrote it this way versus that way. So it is pretty important that we follow these rules because like 3 9s gets you a passing score on most AP chemistry questions. And if one of them is just writing the number right, well, I can do that. You could write, by the way, if this was the right answer, but you wrote 12, you would still get 1 out of 9 because at least you put 2 significant figures. So anyway, moving on. All right. Say that again. Well, chemistry is not the easiest test you'll take, but that part's not that bad. Okay. What's that? Was it? Yeah. Your ability to pass psychology is not a good indicator of AP Chem. The test, at least. They couldn't be more different.
Is it a lot harder than the biology test?
Yeah, because it's math. And there's no writing. So let's pretend you're super good at explaining things. That doesn't matter. There's no more than 2 sentences usually. Then you're probably okay. All right, so here we go. When we read this is a graduated cylinder. We read first from the bottom of the meniscus, this part right here. And then the uncertainty is that we know it's above, this would be 21, it looks like. This would be 22. So we know it's above 21, but we don't know, it's not above 22. So we know it's 21 something, but do we know anything else? No, so we have to guess, and I don't know, it's in the middle, 21.5 milliliters. That number tells me I'm talking about milliliters and that I am around 21 something and that I know it's 21. This would tell the person looking at the cylinder that it was only marked in the tens places right here. Oh, it looks like it goes by twos on this. I didn't look. But, oh, no, that's a 15. I'm blind. So it tells you how accurate the tool was. All right. On the previous slide, if one recorded the volume to be 21.6, 21 are certain, 6 is an estimate. Someone else might say 21.5 or 21.7. They're both right. Well, they're all three right. All the digits in a measurement, including the uncertain last digit, are called significant figures or significant digits, or sig figs for short, is how we refer to them. Frequently, we need to know the number of sig figs in a measurement reported by someone else. Okay. So this is important on how to figure out how many significant figures are in a reported number. So non-zero digits are always significant. So let's say I have 1, 2, 3.5, 6, 7. Since all of these are not the number 0, we would say this has 6 significant figures. Fair enough? Captive zeros are always significant. So let's say we had 120.034. Since these are captive, it means trapped between two non-zeros. They are also significant. And then, this is the only one usually kids screw up, trailing zeros. When they are to the right of a decimal place, they are significant. So if this was 1, 2, 3.456, why did I skip 4 right here? I'm so lost right now. 0, 0, 0. Since these are to the right of a decimal place, they count. This number would have 1, 2, 3, 4, 5, 6, 7, 8, 9 significant figures. And then what do I mean by in scientific notation? We never would, but if I had to write this number right here in scientific notation, it would be 1.2345600 times 10 to the second. If they were in scientific notation, they count as a significant value.
But if they're not,
Then they don't.
So you don't count whatever the 10 is raised to, like the 0.
No.
Okay.
All right. Now, these numbers are always not significant leading zeros. So we mean like 0.0003. That only has one significant figure. Because these are placeholders, but they're not actually telling us anything. It's just making sure we know that it's 3 10,000s. And then trailing zeros when they are to the left of the decimal place. So if I wrote 10,000, this would only have one significant figure. Now, here's annoyingness in science right here. If I had 10,000, and then I had a decimal right here, then this would have 5 significant figures. Now, they don't do that to you very often, but by putting the decimal, we now would say, oh, I know this to this place. But really, AP doesn't do that much. In physics, you'll get this more often. All right. How are you? Lab book? Right over there by the garbage can. They're kind of like spread out, so just grab one of the things. There you go. Okay, so here we go. Here's just an example. We have 3090. This is captive, this is trailing. So tell your partner how many sig figs in this number right here. 3 sig figs. Good answer. Okay, tell your partner how many sig figs in this one. Okay, I heard that answer pretty quick. 4. These don't count. Everything after does. This 0 counted because it was to the right of a decimal. This one did not count because it was to the left of a decimal. Okay. Anybody lost? Yes? More practice? What's that? Over here?
Yeah, the 2 ones after the decimal to the right of the decimal.
They don't care about where the decimal.
Right here? Are you talking these two? I'm sorry. So since they're the leading, they're just helping you move the decimal over, but they're not actually a value. So they don't matter. Go ahead.
Why do the trailing zeros after the decimal matter?
Okay, that's a really good question. Because this 0 tells me I know the 2. If there was no 0, then it would tell me I only knew that number. That arrow didn't point right. And if there wasn't these, then if there's just 0.8, all I would really know is it's some number in the thousands place. So the more we go, the more accurate it is. So that's why they matter. Now, here's the reason why. Well, there's 2 reasons why these are important. If I write this number in significant notation, all 4 of the sig figs have to be put in. 8.020 times 10 to the 1, 2, 3, negative third. This one, it wouldn't really matter, or the 0 doesn't matter. 3.09 times 10 to the 1, 2, 3. So when we report the scientific notation, we only include the significant figures. And so that's why another reason these 2 zeros don't count, because it would look really weird if we put 008.020 times 10 to the negative third. This tells me that there was 2 things before it, so I don't need to put it in there. Did you want more practice? Okay, so let's see. Okay, so with your partner, figure out how many sig figs each one of these numbers have. Okay, anyone disagree? I do make mistakes once in a while, by the way. They look good? Okay. All right, in calculations, which this is pretty important, when you add or subtract numbers, we round the result to the same number of decimal places as the number with the least number of decimal places. That's the least precise value in terms of addition and subtraction. So if it was like 10.1589, that's a 0, plus 1, then the answer is 11. If it was 1.0, then the answer would be 11.2, because it'd be 1, but we'd have to round it up because they have 5. Okay, we find the shortest number and we report the number to that number of decimal places. All right, when we multiply or divide, which we do this one way more often, so this is the important one, we should round the result to the same number of digits as the number with the least number of significant figures. They seem the same, but they are different, I promise. So this one, if we had 3.51 times 2, we would multiply this and we get 7.02, right? But really, since this only has one sig fig, we just say 7. Okay? We'll do a lot of this. A lot. You'll get extremely used to it. And then this just explains rounding, which hopefully you learned a long time before today. And then there's more rounding out of time. So this is talking about density. So we know the mass, so 51.842. Then I have my initial volume and my final volume. To find the volume of just the piece of gold, I subtract, so it'd be 2.7, right? Now you would do the math, but the answer should only have how many total significant figures? 2. Since this one is not as precise as this one, the answer can't be more precise than that. Is that, you okay with that? We'll do a lot more, I promise. This is not the only time we'll go over this. Yeah.
With that, it's just divided it by 2, we still have the 2 in front of it. So would it just be in the place, or would
Say it louder, I'm sorry.
so like when you're dividing it by 2.7, it'd be like 0.5 something. So would the ones before the decimal matter more?
Yeah, so let's say it was 25.834 or something like that. We would say this was 2, so then I would round based on that 8 and just call it 26 grams per milliliter. So do the math and then you round. Okay, we're definitely super out of time. Accurate, you hit what you were going for. Precise, you repeated where you were. Okay, precision means you're able to repeat the measurement. That's in the reading. Is that table in the reading? It's just saying this is not where it's supposed to be, but they're close. So it's precise but not accurate. Number 2 is more accurate but less precise because there's a bigger range, but it's closer than I wanted. And then this, they're all really close. So that's both accurate and precise. And then we definitely didn't get as far as I wanted. This is not in the reading, so we have to go over this together. All right, this weekend, so we're pretty far behind already, which is expected. I mean, we are only meeting every other day. So we will do a lab the next time we get together. Please make sure you've read this. You can do these review problems if you want. I'll grade them, but they're not on your grade. But then in chapter 2, there's a reading guide that I am going to put on your grade, and it's not impossible. It's a little. There's some that are tricky to find, but overall, they're not that bad. And then this is what I want you to start looking at. It's called Elements and Polyatomic Ion Memorization. Please, where'd you go? Please start looking at that. This is not going well. So it's right here at the bottom. Oh, it's not published. I'll publish that. You have to memorize 50 elements in this class and then also a list of polyatomic ions. And that's simply for speed. And the elements are not that hard, I promise. Half of them you'll know. So with this paper, what you can do is you look up chlorine and its symbol, then the polyatomic ions are down here. I won't test this for weeks, but you can start getting on that. There's links to it on Quizlet as well. And then, I don't know. Wow, we're behind.